Please subscribe to support the channel. What actually lies beneath atoms, in that hidden zone where the rules of normal physics collapse and nothing behaves the way we expect? The deeper you go, past molecules, atoms, and the particles inside them, you reach a place where our everyday intuition fails completely. This is the quantum realm, not a sci-fi dimension, but the real universe at its tiniest scale, ruled by quantum mechanics instead of common sense. Down here, particles don't act like solid objects. They flicker, blur, shift, and behave more like possibilities than physical things. They refuse to stay in one spot, sometimes appearing as waves spread across space, sometimes snapping into place only when we try to observe them. And that bizarre behavior sets up our next mystery. Why does something as solid as an electron sometimes act like a ripple instead of a particle? Why does something as tiny and solid as an electron sometimes behave like a ripple spreading across a pond? It sounds impossible, like asking how a marble could suddenly turn into a wave of water. But that's exactly what electrons do when we push them into the quantum realm. And the weirdest part, they don't just behave this way occasionally. This is their natural behavior when nobody's watching too closely. That mystery hit scientists hard when they tried to fire single electrons at a simple experiment. Two tiny slits cut into a barrier. Here's where the tension explodes. When scientists shot a stream of electrons through those slits, they expected the electrons to act like tiny bullets, creating two neat lines on the screen behind them. But that's not what happened. Instead, the electrons built an interference pattern, the exact same pattern you'd get if you were sending waves through the slits. Waves that spread out, overlap, and create bright and dark stripes. Even stranger, when scientists fired one electron at a time, giving each electron plenty of time to travel alone, the interference pattern still appeared over time, as if each electron somehow went through both slits, like a wave, interfered with itself, and only then hit the screen. But when scientists tried to watch which slit the electron actually passed through, the entire pattern changed back to behaving like a particle. It was as if the electron only acted like a wave when nobody was looking. This contradiction, particles behaving like waves and waves behaving like particles, isn't a glitch. It's the heart of quantum mechanics, and it's called wave-particle duality. The idea is simple but mind-bending. Particles aren't strictly particles or waves. They're quantum objects, and they can show properties of both depending on how we observe them. They're not little billiard balls. They're not smooth, rippling waves. There's something deeper, something the human brain was never built to visualize. At this scale, the universe doesn't play by our rules. We have to play by its. And that leads to the stranger question hiding underneath all of this. If particles can spread out like waves, then what does it even mean to say they have a position? Do they actually exist in one place before we look? Or are we completely misunderstanding what location means in the quantum realm? How can something as tiny as a particle exist in multiple possible states at once? It sounds like pure science fiction, like saying an object is both here and over there before you decide to check. But in the quantum realm, that's not exaggeration. That's the rule. When you try to pin down where a particle actually is, you run straight into a wall. The universe refuses to give you just one answer. Instead, it hands you a whole menu of possibilities. This is where classical logic completely falls apart. In our everyday world, things have definite locations. A book on a table isn't maybe anywhere, it's exactly where you put it. But quantum particles don't obey that kind of certainty. When they act like waves, their position spreads out. Their where becomes smeared across space. Not because they're moving too fast to track, but because they genuinely don't have one exact location. If you try to imagine this with normal objects, you'd picture a baseball that could be floating anywhere in a room until the moment you open your eyes. That's the level of weirdness the quantum world deals in. The truth is that particles exist in what we call a superposition, a state where all possible positions exist at once, but only as probabilities. Instead of thinking of an electron as a tiny dot, imagine it as a cloud of maybes. That cloud represents all the places the electron could be, with some spots more likely than others. It's not hiding from us, it genuinely doesn't settle on a single location until the universe forces it to. So when you ask, where is the electron right now, the quantum answer is, everywhere it might be. And here's the part that should make your brain tingle. This cloud of possibilities snaps into a single location the moment we observe it. It's as if reality waits for someone to look before choosing an outcome. But how? How can simply observing something change what it is? Why do particles seem to decide what they are only when we look at them? It's one of the most unsettling mysteries in all of physics because it makes reality feel like it's somehow waiting for us, like the universe is holding its breath until someone checks in. In the quantum realm, particles wander in a haze of possibilities, acting like waves that spread out across space, but the moment we try to measure them, whether it's their position, their path, or even which slit they went through in an experiment, they suddenly snap into a single definite state. It's as if the universe says, "Oh, you're watching? Fine, here's one answer." And that simple act of looking changes the outcome. But why? Why does measurement have such a powerful effect on something so tiny? The tension here gets even stranger when you dig into the measurement paradoxes that physicists have wrestled with for decades. For example, consider the double slit experiment again. When we don't observe the electrons, they behave like waves, passing through both slits and creating an interference pattern. But the instant we place a detector near the slits to check which path they take, the interference vanishes and they behave like particles instead. Nothing physical has changed about the electrons, only the fact that we're observing them. In quantum mechanics, the act of measurement isn't passive. It doesn't just record reality, it creates the reality we end up seeing. This raises uncomfortable questions about what's actually happening when nobody is watching. Is the electron really in all those possible states at once? Or is the wave simply a way to describe our lack of knowledge? And if it's truly in multiple states, what does it mean for reality itself? The most accepted explanation is something called wave function collapse. The wave function is just the mathematical description of all the possible states a particle can be in, its whole cloud of maybes. When the particle is left alone, that wave function spreads out, representing all those simultaneous possibilities. But when a measurement happens, the wave function suddenly collapses to a single state. Before measurement, the particle isn't choosing between options. It is the options. After measurement, it becomes just one. This collapse isn't something we fully understand. It doesn't come from physical forces or classical interactions. It's like a rule baked into the universe. Once information about the system becomes available, the system must settle on one outcome. And the implications get even wilder. If observation can change what a particle becomes, then what happens when two particles are linked, when their fates are tied together no matter how far apart they are? Could observing one instantly affect the other, even across galaxies? Because in the quantum world, particles don't always act alone. Sometimes they remain connected across impossible distances in a way that seems to break every rule we know about physics. So the next question becomes almost unbelievable. How can two particles stay perfectly linked, mirroring each other instantly, even when separated by vast distances? How can two particles mirror each other instantly, no matter how far apart they are? This isn't a comic book superpower or some secret sci-fi communication trick. This is a real effect observed in laboratories around the world. Imagine you create a pair of particles that are born together, like twins. You separate them. One stays on Earth, the other you send to the opposite side of the galaxy. Then, at some random moment, you measure one of them. Instantly, the other particle reacts as if it somehow knew what you just did, even though no signal could possibly reach it in time. Something connects them, Something deeper than space, deeper than distance. Einstein hated this idea so much he called it spooky action at a distance because according to classical physics, it should be completely impossible. And that's where the tension skyrockets. Under normal physics, the kind we're used to, information cannot travel faster than the speed of light. That's not just a rule, it's the rule. It's the cosmic speed limit, the thing that keeps cause and effect from turning into chaos. But entangled particles somehow coordinate instantly, with no message passing between them, no signal carrying the news, and no time delay at all. If one particle ends up spinning up, the other ends up spinning down, even if they're millions of miles apart. But they don't decide these spins ahead of time. Experiments prove they don't carry hidden instructions. They really only pick their states at the moment of measurement. Yet, the matching result is always perfect. It's like flipping two coins separated by galaxies and watching them land on matching sides every single time. Not sometimes, always. Classical physics has no explanation for this. It breaks the idea of locality, the assumption that objects can only be influenced by things physically nearby. It bends the idea of realism, the belief that objects have definite properties before we measure them. Entanglement shatters both. The reveal is as simple as it is mind-warping. Entanglement isn't about communication between particles. It's about them sharing a single quantum state. They aren't two separate things acting in sync. They are parts of one larger system. When you measure one particle, you're not sending information to the other. You're collapsing the entire shared quantum wave function. Think of the entangled pair not as two coins, but as one coin stretched across space. When you flip one side, you're really flipping the entire quantum object, so the other side reflects the change instantly. The universe doesn't treat them as two particles. It treats them as a single, inseparable unit, even across unimaginable distances. That's why no message is transmitted. The two outcomes are born from the same underlying reality. Quantum mechanics doesn't care about distance the way we do. It doesn't care about separation. If two particles are entangled, space between them simply doesn't matter in the way we intuitively think it should. And here's where things twist even further. Entanglement is not some rare, exotic phenomenon. It happens all the time, inside atoms, inside materials, inside the photons bouncing around your room. It's built into the fabric of reality. And even stranger, entanglement is only one of several bizarre kinds of quantum connections that shape the universe at the smallest scales. Because if two particles can share a state across galaxies, then what does that say about what particles actually are in the first place? Are they even objects at all? Or are they something more like ripples in a deeper ocean? That leads us straight into an even bigger question. If particles behave this strangely, what are they actually made of? Are they tiny balls of matter, or are they something more fundamental? What are particles actually made of? It sounds like a simple question. Tiny objects should have tiny parts, right? But the deeper physicists looked, the more that idea started to fall apart. Electrons, quarks, photons, none of them behave like small, solid balls of matter. They don't have little surfaces or cores. They don't spin like tops. They don't even sit still like objects should. Calling them particles is almost misleading. It suggests a little bead or dot you could hold in your hand if only you were small enough. But when scientists tried to understand particles that way, nothing added up. Their behavior was too weird, too flexible, too wave-like, too tied to invisible forces and interactions. Something about the entire picture was off. The tension gets stronger once you consider how impossible it is for these so-called tiny balls to create the effects we observe. How does a perfectly round little object simultaneously behave like a spread-out wave? How does it interfere with itself when it travels alone? How does it instantly influence a partner on the other side of the universe? Classical pictures break down instantly. Even the idea that a particle has a precise boundary or size stops making sense. Instead, particles behave more like patterns, like temporary disturbances that appear, interact, and vanish. When you push them, they don't roll or bounce, they ripple. When you confine them, they don't shrink, they shift into new configurations. And the more we measure them, the more they look like something emerging from a deeper, hidden layer of reality rather than fundamental objects themselves. That's where the big reveal comes in. Particles aren't things the way we imagine them. They're excitations, vibrations of underlying quantum fields that fill the entire universe. Imagine an ocean that covers everything, everywhere, all the time. Now imagine a wave rising on the surface of that ocean. That wave is like a particle. The ocean underneath is the field. Every type of particle has its own field, an electron field, a quark field, a photon field. These fields stretch across all of space, even the emptiest vacuum. And a particle is just a tiny disturbance in one of those fields. It's not made of anything. It is the field behaving in a certain way. An electron isn't a mini marble. It's a ripple of the electron field. A photon isn't a bead of light. It's a vibrational blip in the electromagnetic field. When we talk about particles popping into existence or vanishing, we're really talking about fields turning their ripples on and off. This changes everything about how we understand matter because it means the universe is fundamentally made of fields, smooth, continuous, invisible structures that extend everywhere. And particles are just the temporary, localized excitations riding on top of them. This explains why particles can behave like waves or dots or vanish or reappear or remain connected across vast distances because they aren't standalone objects. They're patterns in these universal fields. Patterns can spread out, patterns can overlap, patterns can connect instantly because the field underneath them is already unified across space. But here's the twist that sets up the next dark corner of the quantum world. If fields fill the entire universe, then what does empty space actually mean? If fields are everywhere, can emptiness even exist? Because when physicists looked closer, they found that the vacuum, the place we assume is totally nothing, isn't empty at all. It's one of the most active, energetic, seething places in reality. Which brings us to the next question. How can pure nothingness be boiling with activity and energy? How can nothingness possibly boil with activity? If you imagine empty space, you probably picture a silent void, dark, motionless, completely blank. But in the quantum realm, that ideal falls apart instantly. When physicists try to understand what the universe is like when you remove all particles, all fields, all radiation, everything, they discover something shocking. The vacuum never sits still. Even when there's nothing, there's something. Space itself vibrates, fluctuates, and churns with hidden energy. So the real mystery becomes, how can emptiness be one of the most restless and energetic places in the universe? The tension builds when you look at what's known as zero-point fluctuations. Quantum mechanics says that every field that exists, electron fields, photon fields, quark fields, must always have some minimum amount of energy, even when they're in their lowest possible state. They can't be perfectly still. They can't be perfectly flat. They can't reach true zero. This is because if a field ever stopped fluctuating completely, you could know both its energy and its precise state with total certainty, and the uncertainty principle forbids that. So instead, even the calmest, most empty region of space jitters with tiny vibrations. These fluctuations aren't optional. They're a fundamental part of how the universe works. They happen everywhere, all the time, and they never stop. Even in regions of space that have been cold and empty for billions of years, the quantum fields there continue to twitch and buzz. And here's the big reveal. Those tiny fluctuations constantly create pairs of virtual particles, little bursts of matter and antimatter that pop into existence and then annihilate each other almost instantly. These aren't particles you can hold or detect directly, because they appear and vanish faster than any instrument can track them. But their effects are real, measurable, and unavoidable. Virtual particles affect the forces between atoms. They shift the energy levels of electrons. They even help explain why magnets and electric fields behave the way they do. The vacuum isn't empty. It's a sea of constant creation and destruction, a background storm of momentary blips of energy. This vacuum energy might even be responsible for the expansion of the universe itself. The void is alive, not in a biological sense, but in a quantum mechanical one. The emptier the space, the more fiercely quantum mechanics refuses to let it rest. And this sets up the next incredible twist. If the vacuum is filled with these virtual particles, tiny ghosts that appear and vanish, what exactly are they? How do they shape the forces between particles? Why do they matter so much to the structure of the universe? These flickering bursts aren't just a footnote to physics. They're one of the keys to understanding how all interactions actually work. So the next mystery we need to unravel is, what are these strange particles that pop in and out of existence faster than we can even define them. How can particles appear out of nowhere and then disappear before they even have time to fully exist? That's the unsettling mystery at the heart of virtual particles. Fleeting blips of matter and energy that erupt from the vacuum, live for a tiny fraction of a second, and then vanish as if they were never there. They're not like normal particles you can trap, detect, or isolate. They're ghosts of the quantum realm, flickering in and out of reality so quickly that you can't point to them and say, "There, that's one." And yet, somehow, these near imaginary particles quietly shape almost every fundamental process in the universe. The idea sounds ridiculous at first. How can something that doesn't technically exist still influence everything that does? The tension builds once you examine how forces actually work. In our everyday world, we think of forces as pushes and pulls. Gravity makes things fall. Magnetism makes objects attract or repel. Electricity flows along wires. But in quantum mechanics, forces aren't continuous fields acting across space. They're the result of particles exchanging virtual particles. When two electrons repel each other, they do it by tossing virtual photons back and forth. When quarks stick together inside a proton, they're glued by virtual gluons. Even the weak nuclear force which causes radioactive decay is carried by virtual W and Z bosons. These virtual messengers pop into existence just long enough to do their job, then disappear before the universe notices they broke the rules. And the only reason the universe allows this at all is because of the uncertainty principle. For tiny enough periods of time, energy can appear from nowhere as long as it returns back to nothing before the universe demands an accounting. It's like borrowing energy with a deadline so strict that the moment you reach it, the loan vanishes automatically. Here's the big reveal. Virtual particles are not real in the ordinary sense, but they are very real mathematically and physically. They're temporary fluctuations in quantum fields, tiny disturbances that arise because the fields can never be perfectly still. These disturbances show up in equations as particles, even though they exist for such a short time that they can't be directly observed. They're like brief ripples caused by the restless nature of the quantum vacuum. Their presence explains shifts in atomic energy levels, the behavior of magnets, the strength of electromagnetic forces, and even the stability of matter. Without virtual particles, atoms wouldn't stay together. Forces wouldn't exist. The universe as we know it would collapse instantly. They may be temporary, but their effects are permanent and profound. And here's where things get even stranger. If the vacuum is constantly boiling with virtual particles, popping in, disappearing, reappearing, swirling, and overflowing with energy, then what happens when you zoom in far enough to see the chaos directly? What does space look like when you reach the smallest scales where these fluctuations twist and stretch space-time itself? Because the closer you get to the foundation of reality, the more the vacuum stops looking like empty space and starts looking like a storm of bubbling, warping geometry. Which leads to the next big question. What happens when virtual particles and vacuum energy distort space-time so violently that space itself becomes foamy and chaotic? What does space-time actually look like when you zoom all the way down to the smallest scale imaginable? Not the scale of atoms, or even the particles inside them, but the true basement of reality, the Planck scale. At human size, space feels smooth and steady. Even when you shrink down to molecules or electrons, everything still seems like it exists on solid ground. But if you keep zooming deeper and deeper, there comes a point where the very fabric of space stops acting like a stable stage and starts behaving like something wild and unpredictable. So the question becomes, if space and time are usually the grid that everything else sits on, what happens when that grid becomes unstable? The tension ramps up once classical concepts like distance and time begin to lose meaning. On the smallest scales, you can't say where something is with perfect accuracy. Uncertainty smears everything out. Trying to measure a tiny distance adds so much energy to the space you're examining that you might actually create a tiny black hole, erasing the very region you're trying to observe. Time becomes jittery, refusing to flow smoothly from one moment to the next. Distances shrink and expand unpredictably. The neat picture of space-time as a calm continuous fabric, like a sheet woven tightly and evenly, completely collapses. Instead,
Quantum fluctuations yank and tug on the geometry itself. Every point in space wriggles, every tiny interval of time flickers. The background of reality becomes a chaotic storm of jittering, boiling geometry. The universe stops looking like a smooth landscape and starts looking like a turbulent sea. And here's the reveal physicists arrived at. At the smallest scales, space-time becomes a bubbling, frothing mess known as quantum foam. Imagine the surface of boiling water, constantly popping with bubbles, rising and collapsing in unpredictable ways. Now imagine that this chaotic bubbling happens to space itself. Tiny fluctuations in energy create miniature distortions, microscopic twists, warps, dips, and peaks. Space-time curves, uncurves, folds over itself, and vibrates in patterns too fast and too small for any instrument to record. In this foamy structure, here and there blur together. Tiny wormhole-like distortions flicker in and out. Minuscule pockets of space expand, contract, or collapse in the blink of an eye. This is not science fiction. This is the prediction of quantum gravity merged with quantum mechanics. At this level, space is not a smooth stage. It is a restless, shifting storm of geometric flickers. Quantum foam might sound like an obscure idea, but it has huge implications. If space is constantly bubbling with tiny distortions, then particles moving through it are influenced by that chaos. Sometimes the foam opens microscopic shortcuts. Sometimes it momentarily weakens barriers. Sometimes it creates just enough instability for a particle to slip through places it shouldn't be able to pass. The foam is like a constantly shifting puzzle that particles have to navigate, and sometimes the fluctuations create opportunities that would be impossible in a smooth classical world. The more chaotic the foam, the more likely particles are to do unpredictable things. Which naturally leads to the next mind-bending question. If space-time is this unstable and jittery, could that be why particles sometimes pass straight through barriers they shouldn't be able to cross? How does a particle tunnel through something that should stop it cold? How can a particle pass straight through a barrier that should absolutely block it? At our scale, that's impossible. If you throw a ball at a wall, it doesn't magically appear on the other side. If you try to walk through a locked door, you don't suddenly melt through it. Classical physics is very clear. If you don't have enough energy to cross a barrier, you stop. End of story. But in the quantum realm, that rule simply doesn't hold. Electrons, protons, and other tiny particles sometimes appear on the far side of barriers they have no business getting through. It's like watching reality glitch, as if the universe suddenly decides to ignore its own laws. Except, this isn't a glitch at all. It's a fundamental feature of how nature works when you zoom in far enough. So how does something go from blocked to somehow on the other side? The tension grows when you compare what should happen to what does happen. Classically, a particle facing a barrier, say a thick wall or an energy hill, should reflect back if it doesn't have enough energy to cross it. Picture a skateboarder rolling toward a ramp. Too little speed and they roll back down. That's how things behave in our everyday world. But quantum particles don't act like tiny skateboarders. They don't sit at one exact location, and they don't follow a single defined path. Their existence is smeared out into a wave of probabilities, and waves behave very differently from solid objects. When a wave hits a barrier, part of it reflects, but part of it can leak through. Even if the barrier should be completely impossible to pass, the wave still has a tiny chance of appearing on the other side. And if the wave can make it, then the particle, because it is the wave, can make it too. The classical rules that stop everything on our scale simply don't stop the quantum world. The reveal is this. Quantum tunneling happens because particles are described by wave functions, mathematical waves that represent all the places the particle could be. When a particle encounters a barrier, its wave function doesn't just stop at the wall. It fades inside it and sometimes reappears beyond it. That faint teal of probability behind the barrier means there is always a small but real chance the particle will show up on the far side, not by breaking the barrier, not by slipping through a hole, not by smashing its way across. Instead, the particle simply exists on the other side because the wave function allows it. It's not teleportation, and it's not cheating. It's just the way quantum probability works. The particle never had to travel through the barrier in a classical sense. It lived as a cloud of possibilities the whole time, and one of those possibilities extended beyond the wall. Every so often, the universe chooses that possibility, and the particle appears where logic says it shouldn't. And here's where things get truly staggering. Quantum tunneling isn't just a weird trick of tiny particles. It's responsible for some of the most important processes in the universe. Without tunneling, atoms wouldn't form the way they do. Radioactive decay wouldn't happen the same way. Electronics wouldn't function. And far more dramatically, stars, including our sun, would never ignite. The cores of stars are far too cool, in classical terms, for fusion to start. Protons should repel each other so strongly that fusion becomes impossible. Yet stars shine every day. Which brings us to the next massive mystery. How does quantum tunneling allow the sun to burn when classical physics says fusion shouldn't happen at all? How does the sun fuse atoms together when its core isn't nearly hot enough to overcome the powerful repulsion between positively charged particles? This is the heart of one of the greatest puzzles in astrophysics. Inside the sun, hydrogen nuclei, protons, should repel each other so fiercely that they could never collide, never merge, never fuse. Classical physics says the sun should be dark and cold, because the temperatures in the core, while extreme by human standards, are still far too low to push protons close enough for the strong nuclear force to grab them and weld them together. Every proton in the sun is like a tiny magnet with the same pole facing outward. They repel, they resist, and they should bounce away from each other forever. So the question becomes, if the sun doesn't have enough classical energy to force fusion, why is it glowing with such incredible power? The tension rises once you realize how big the gap is between what should happen to what does happen. At about 15 million degrees Celsius, the sun's core is imaginably hot, but not nearly hot enough for classical fusion. Protons need to get close enough for the strong nuclear force to overpower their electric repulsion. But to reach that distance by classical means, the core would need temperatures in the billions of degrees. That's not even remotely close to reality. According to classical physics, the sun is a failed fusion reactor. It should never have ignited. It should never have shone. It should never have formed the elements needed for planets, life, or anything stable. Yet, it clearly burns, pushing out enormous amounts of energy every second. The sun is a paradox, a star that should not exist, burning through a process that classical physics cannot explain.
The reveal flips that paradox on its head. The sun shines because of quantum tunneling. Even though protons in the core don't have enough classical energy to slime into each other, they do have wave functions, those probabilistic quantum waves that smear out their positions. When those wave functions overlap, there is a small but incredibly important chance that one proton's wave will extend past the repulsive barrier surrounding another proton. In other words, the proton tunnels through the barrier it should not be able to cross. It doesn't need enough energy to climb over the barrier, its wave function simply leaks through it. And when that happens, when two protons suddenly appear close enough together inside that barrier, the strong nuclear force snaps them into a fused state. This quantum shortcut allows fusion to occur at temperatures billions of degrees lower than what classical physics would require. It's not a rare trick either. It's happening trillions of times every second inside the sun. Quantum tunneling keeps the sun burning, and without it, hydrogen would never fuse into helium and the universe would be a dark, cold place with no stars, no warmth, and no complex elements. And here's the part that ties everything together. Tunneling isn't just enabling fusion, it's revealing how deeply quantum forces shape all matter. The sun's energy, the formation of heavier elements, the chemistry that built planets, the biology that builds life, all of it flows from quantum rules operating at the tiniest levels. The same quantum mechanics that lets particles tunnel through barriers also governs how forces bind nuclei, how atoms form, how molecules hold together, and how matter behaves in every corner of the universe. So that brings us to the next big question. If quantum effects power the sun and hold matter together, how do the four fundamental forces themselves behave in the quantum realm? How do the fundamental forces of nature operate when you shrink the universe down to the tiniest possible scales? We know how forces behave in the world we see. Electricity shocks, magnets pull, gravity keeps our feet on the ground. But in the quantum realm, none of those forces act the way we expect. At that microscopic level, every force is no longer a smooth push or pull. Instead, it becomes a chaotic exchange of quantum particles interacting through fields that flicker and fluctuate. The deeper you zoom in, the more the familiar picture of forces breaks apart. So the question becomes, when matter shrinks to its smallest form, what do forces even look like? The tension ramps up when you realize that our best theory of gravity, general relativity, doesn't fit into this quantum picture at all. Electromagnetism, the weak force, and the strong force all have quantum descriptions that rely on particles exchanging virtual messengers. But gravity, the force that shapes planets, stars, black holes, and the entire expansion of the universe, refuses to cooperate. When you try to quantize gravity, when you try to describe it using the same mathematics that works beautifully for the other forces, everything breaks. The equations explode into infinities that cannot be canceled out. Predictions fail. Mathematical tools that work perfectly for other forces collapse instantly when applied to gravity. For nearly a century, every attempt at building a quantum theory of gravity, string theory, loop quantum gravity, extra dimensions, emergent spacetime, has offered hints but no final answer. Gravity sits outside the quantum club, refusing to join, and the universe will not tell us why. But there is a potential reveal, a hypothesis that might bridge the two worlds, something called the graviton. If the other forces are carried by particles, maybe gravity has a carrier too. A graviton would be a massless spin-2 particle that transmits gravitational interactions the same way photons transmit electromagnetic ones. If gravitons exist, gravity would finally have a quantum description. They would ripple through space-time as tiny vibrations, linking masses across the universe through quantum exchanges. But here's the catch. No experiment has ever detected a graviton. Not one. They would be incredibly weak, barely interacting with anything, so subtle that even the most sensitive detectors humanity has built might never see one. The idea is mathematically beautiful, but experimentally invisible. We're left with a theory that could fix everything if only we had a shred of proof. And here's the twist that deepens the mystery even further. Gravity resists quantization because it interacts directly with space-time itself, and space-time becomes wildly unstable at extremely tiny scales. The closer you get to the Planck length, the more quantum uncertainty starts ripping the smooth fabric of space-time apart. Distances fluctuate, time flickers, geometry becomes unpredictable. It might be the quantum uncertainty principle itself that prevents us from pinning down gravity in the same neat way we do with other forces. Which leads us straight into the next profound puzzle. Why does nature place strict limits on what we can know? Limits so deep that they make the very fabric of reality jitter and fluctuate. Why does nature prevent us from knowing certain things at the same time, no matter how advanced our technology becomes? Why can't we measure both the exact position of a particle and its exact momentum simultaneously? Why can't we freeze the universe into a perfectly clear snapshot with all information laid out cleanly? It feels almost unfair, like nature has hidden some of its most basic truths behind a cosmic privacy filter. But this isn't a problem with our tools, our experiments, or our imagination. It's a built-in limit, a fundamental rule of the universe that says you can know one thing precisely, or the other precisely, but never both. And the closer you try to get to perfect knowledge, the more the universe pushes back. The tension gets even stronger when you think about how measurement works at small scales. In the everyday world, measuring something doesn't change it in any important way. You can check the temperature of your coffee without altering its flavor. You can weigh a book without moving the words on the pages. But in the quantum world, measurement is interaction,
forceful, unavoidable interaction. To see an electron's position, you have to hit it with a photon. But that photon carries momentum, and even one tiny push from it changes the electron's motion. The moment you focus more precisely on where the electron is, you disrupt how it's moving. And if you try to measure its momentum with extreme accuracy, you have to back off from pinning down its location. It's not a flaw in the instruments, it's the way the universe is built. Perfect measurement is impossible because measuring at all changes the system you're trying to measure. And here's the reveal at the heart of this strange behavior, the Heisenberg uncertainty principle. It states that you can't know a particle's exact position and exact momentum at the same time. The more precisely you know one, the other becomes fuzzier. And this uncertainty isn't because the particle is too small or because our tools disturb it too much. It's because particles fundamentally don't have exact positions or momenta at the same time. They exist as probabilities, spread out in clouds of possible values. The wave function that describes a particle doesn't give definite answers. It gives a range of possibilities. When you force the wave function to collapse into a precise position, the momentum becomes wildly uncertain, and vice versa. The universe simply does not allow perfect sharpness in both properties. This principle explains why particles in the quantum realm behave so chaotically. Because their positions and energies can never be perfectly fixed, particles constantly jitter, flicker, and wiggle in unpredictable ways. Even if you cooled a particle to absolute zero, removing all the classical energy you could possibly remove, it would still fluctuate because uncertainty requires it. These fluctuations aren't noise, they aren't mistakes. They're the engine of the quantum world, driving everything from particle motion to the restless activity of the vacuum itself. Particles are wild because uncertainty forces them to be wild. And this brings us face to face with the next mystery. If uncertainty makes particles jitter, flicker, and fluctuate, even in perfect vacuum, what exactly are these wild quantum fluctuations, and why do they seem to arise from nowhere? How can randomness exist at the very foundation of physical law? We're used to thinking that if you know enough about a system, its position, speed, environment, you should be able to predict exactly what it will do next. That's classical thinking. But in the quantum realm, that laughs at that idea. At the smallest scales of existence, randomness isn't a mistake or a side effect. It's woven directly into the fabric of reality. Particles don't simply move from point A to point B. Instead, they jitter, flicker, appear, vanish, and reappear in ways that seem completely unpredictable. And the deeper you zoom into the quantum world, the more you realize that randomness isn't something layered on top. It is the operating system of the universe itself. So the question becomes, where does this randomness originate, and why does nature allow such wild behavior at microscopic scales?
The tension rises once you examine how particles behave when left completely alone. Imagine isolating a single electron in the darkest, coldest, emptiest vacuum possible, a perfect laboratory for stillness. You might expect it to freeze into place, unmoving and silent, but that never happens. The electron still vibrates, shifts, and fluctuates. It refuses to remain at rest. Even the vacuum surrounding it buzzes with unpredictable activity, popping with temporary particles and wild bursts of energy. At tiny scales, predictability breaks down so completely that you can't even say with confidence where a particle will be a moment from now. You can only calculate the probabilities of where it might be. The universe at this level behaves like a storm of possibilities, each flickering in and out faster than thought. This isn't randomness caused by chaos or disorder. It's deep, intrinsic unpredictability built into the core structure of spacetime. Here comes the reveal. Quantum fluctuations are not glitches. They are essential features of the universe. They arise because of the uncertainty principle itself. If particles could settle into perfectly fixed states, exact position, exact momentum, exact energy, the laws of quantum mechanics would collapse. Uncertainty demands motion. It demands variation. It demands that fields and particles never reach absolute stillness. So fields quiver, particles jitter, even empty space boils. These fluctuations allow particles to tunnel through barriers, allow virtual particles to appear and disappear, and even help determine the arrangement of electrons inside atoms. If you tried to remove quantum fluctuations, atoms would fall apart. Matter as we know it would cease to exist. The universe depends on these tiny bursts of randomness to remain stable and dynamic.
And these fluctuations don't just influence particles, they create entire exotic states of matter. When atoms or particles are cooled, squeezed, or arranged just in the right way, their quantum jittering can sync up, producing new forms of matter that behave in ways totally unlike everyday solids, liquids, or gases. Some states act like giant single particles. Some conduct electricity without resistance. Some defy classical rules about motion and stability. These exotic phases emerge because quantum fluctuations never turn off. They only change how they organize. Which leads directly to our next mind-bending question: what happens when atoms become so cold and so synchronized that they behave like one giant wave instead of many individual particles? What happens when atoms stop acting like individual particles and instead merge into one giant quantum wave? This is one of the strangest, most beautiful transformations in all of physics. A moment when matter abandons its everyday identity and becomes something entirely different. Normally, atoms behave like tiny independent dots bouncing around, each with its own energy and motion. But under the right conditions, they can lose that individuality completely. They can overlap, synchronize, and behave as if millions of atoms are a single unified entity. It's like watching an entire crowd suddenly move with one mind, one rhythm, one identity. But this bizarre state of matter doesn't happen naturally. You have to push the universe into an extreme corner to make it show itself. And here's where the tension climbs. To coax atoms into acting like one giant wave, you must cool them to temperatures unimaginably close to absolute zero, the coldest possible temperature in the universe, where thermal motion nearly stops. Not minus 100 degrees, not minus 1,000, we're talking billions of a degree above absolute zero. At these temperatures, atoms move so slowly that their individual wave functions, the quantum wave that describe each particle's position and momentum, begin to overlap. But getting there is absurdly difficult. You need lasers tuned with insane precision, magnetic traps stronger than anything you'd use in daily life, and vacuum chambers emptier than interstellar space. Even a single stray molecule of air bumping into the atoms can destroy the whole process. It's a delicate operation where the slightest disruption shatters the state you're trying to create. Yet, if you manage to cool the atoms enough, something extraordinary happens. They stop behaving like separate entities and merge into one collective wave. And that's the reveal. A Bose-Einstein condensate is a state of matter where millions, even billions of atoms occupy the same quantum state. They become one giant shared wave function. Instead of individual motions, they move in perfect unison. Instead of acting like a gas, they behave like a single quantum object that you can literally see with your own eyes. In this form, matter loses all the properties we normally associate it with. The atoms are not distinguishable. Their positions blur into the same probability cloud. If you disturb one part of the condensate, the entire thing reacts instantly, like plucking a single string that makes an entire instrument vibrate. BECs flow without friction, they climb walls, they defy gravity. They are macroscopic demonstrations of quantum mechanics, quantum behavior scaled up so large that a camera can capture it. In a BEC, the line between particle and wave disappears entirely because the entire collection is a wave. But here's the twist. Not all particles can form Bose-Einstein condensates. Only particles called bosons, particles that don't mind sharing a quantum state, can merge in this way. The other major family of particles, fermions, follow a very different set of rules. They can't share states, they can't overlap their wave functions, they can never behave like a single giant wave. Instead, they push against each other, resist crowding, and build the structure of matter in a completely different way. And their refusal to share is actually the reason matter is stable and solid. So the next question becomes, what makes fermions so different from bosons, and why do they insist on following a rule that stops them from ever occupying the same quantum state? Why doesn't all matter in the universe just collapse into a single point? If gravity is constantly pulling everything inward, and if atoms are mostly empty space, why don't electrons, protons, and neutrons simply fall together into one ultra-dense blob? This sounds like a strange question, but it cuts straight to the reason you have a solid body, a solid planet beneath your feet, and a stable universe around you. If nothing stopped particles from crowding into the same state, all electrons would fall into the lowest possible energy level of every atom. All matter would shrink into an unimaginably tiny point. Atoms wouldn't have size. Chemistry wouldn't exist. Stars and planets couldn't form. So what's stopping everything from collapsing? Why isn't the universe a single pile of overlapping particles?
The tension builds when you imagine what happens inside atoms. Electrons circle nuclei not as little balls, but as wave-like clouds of probability. If these electrons were free to pile into the lowest energy state, every electron in the universe would settle into the same spot, right up against the nucleus, because that's where they'd have the least energy. But that doesn't happen. Instead, electrons stack into different shells and orbitals. They arrange themselves in structured layers. They resist crowding. They feel pressure even without touching each other. In stars, this resistance becomes so powerful that it can support entire collapsed objects like white dwarfs against gravity. Clearly, something fundamental is preventing particles from stacking on top of one another and collapsing into nothingness. The question is, what rule is enforcing this structure? That rule is the reveal, the Pauli exclusion principle. This principle applies to fermions, the family of particles that includes electrons, protons, neutrons, and quarks. It states that no two identical fermions can occupy the same quantum state at the same time. Not prefer not to, not usually don't, they cannot. It is an absolute rule built into the nature of reality. If one electron occupies a certain energy level with a certain spin, no other electron is allowed to take that exact state. To exist in the same region, fermions must differ in something: energy, spin direction, orbital shape, anything. If they can't, one of them is forced to move up to a higher state. This rule is why atoms have multiple shells. It's why elements have specific chemical behaviors. It's why solid matter doesn't collapse. It's even why white dwarfs and neutron stars can resist gravitational collapse. Electron and neutron degeneracy pressure, the quantum pushback created by the exclusion principle, literally holds stars up. The exclusion principle is not just a technical detail. It is the reason the universe has structure. Without it, tables wouldn't be solid, you couldn't stand on the ground, matter would pass through itself, everything would collapse into a dense quantum mush. Bosons can overlap and merge into one giant wave, as they do in Bose-Einstein condensates, but fermions refuse. They insist on keeping their individuality, maintaining distinct states, and resisting collapse. This stubbornness creates the architecture of reality. But fermions aren't just defined by exclusion. They're also defined by another strange quantum property that has nothing to do with spinning in the traditional sense, yet controls how they behave in magnetic fields, how they align, and how we build technologies like MRI machines and quantum computers. So this leads to our next question. How can a particle have spin without actually spinning, and what does this bizarre property really mean in the quantum world? How can a particle have spin without actually spinning? It sounds completely contradictory, like saying a ball is rotating even though it's perfectly still. In everyday life, spin is simple. Something rotates around an axis. But in the quantum world, particles like electrons, photons, and quarks have spin even though they aren't tiny spheres or objects with physical surfaces. They don't twirl, they don't rotate, they don't move around their own centers the way planets or tops do. And yet their spin determines how they interact, how they align in magnetic fields, and how they behave in atoms. So what does it even mean for a particle to have spin if it isn't literally turning? The tension grows once you try to picture it using classical thinking. If you imagine an electron as a tiny ball that spins rapidly, you quickly run into absurdities. To generate the magnetic moment that electrons have, a classical spinning electron would have to rotate faster than the speed of light, an impossible scenario. It would need to be smaller than anything physically meaningful. It would require properties that violate the very laws of physics. The math simply doesn't fit. And yet, electrons behave as if they have angular momentum and a magnetic moment. They behave as if they have spin. This contradiction makes it clear quantum spin cannot be visualized using everyday rotation. It's something deeper, more fundamental, and completely unlike anything we can picture in the macroscopic world. Here's the reveal. Quantum spin is an intrinsic property of particles, meaning it's built into their very identity. Just like mass and charge, spin is a fundamental attribute that doesn't come from motion, it comes from the structure of the particle itself. Spin controls how particles interact with magnetic fields, how they behave inside atoms, and how they combine to form different types of matter. It also determines whether a particle is a fermion,
a half-integer spin, or a boson, an integer spin, which completely changes how it behaves. Spin is tied to deep symmetries in the universe, showing up in the mathematics of quantum mechanics as measurable angular momentum, even though nothing is actually spinning. When you flip the spin of an electron, you aren't twisting it like a top, you're changing a fundamental orientation encoded in its quantum state. And this strange property has become the foundation of one of the most revolutionary technologies humans have ever attempted to build: quantum computers. In these machines, spins don't just determine behavior, they store information. An electron's spin up and spin down states can act as the 0 and 1 of a quantum bit, or more accurately, a blend of both at the same time thanks to superposition. Quantum spin becomes not just a physical property, but a tool for encoding and manipulating information in ways that classical computers can't touch. Which brings us to the next major question. How can information itself exist in multiple states at once, and how do qubits use quantum behavior to outperform classical bits?
How can information exist in multiple states at once? In the classical world, that question doesn't even make sense. A light switch is on or off. A bit in your computer is a 0 or a 1. Your phone doesn't ever store maybe 3, maybe 9. It stores definite values. Classical information is crisp, solid, and unambiguous. But in the quantum world, information doesn't obey those rules. Instead, it can blur, mix, and overlap. A quantum bit, a qubit, can be in the state 0, the state 1, or both at the same time, in a single unified state. It holds possibilities, not just facts. And that raises a mind-bending question. How does the universe allow information to be both definite and indefinite at once? The tension spikes when you compare qubits to classical bits. A classical bit is a tiny switch on a microchip that can only be flipped one way or the other. If you want to explore multiple possibilities, you must check them one at a time, step by step, state by state. That's why classical computers, no matter how powerful, grind through long lists of operations. But a qubit doesn't follow that rigid structure. Because of superposition, a qubit can occupy many potential states at once. Instead of doing one calculation at a time, a quantum computer with multiple qubits can explore a vast number of possibilities simultaneously. Add more qubits, and the number of possible simultaneous states grows explosively, doubling with each qubit. At 300 qubits, a quantum computer could hold more states than there are atoms in the observable universe. Classical computers can't even approach that. The math alone breaks them. Now here's the reveal. Qubits work because quantum systems allow superposition and entanglement. Superposition lets a qubit sit in a mix of 0 and 1 until it's measured. Think of it like a coin spinning in the air, both heads and tails, not one or the other. But entanglement is even more powerful. When qubits become entangled, their states depend on each other completely. Change one, and the other reacts instantly, even if it's far away. Entanglement allows quantum computers to link qubits in patterns that classical bits could never replicate. These shared states let quantum algorithms perform operations that would take classical machines thousands of years. With superposition providing parallelism and entanglement providing coordination, qubits become tools that can crack problems previously thought impossible. But the weirdness doesn't stop with computing. If entanglement allows qubits to share information in ways classical bits never could, what does that imply for communication itself? Can quantum information be transferred without moving anything physical? Can a quantum state be moved from one location to another instantly? It turns out yes, but not in the way sci-fi imagines. So the next question becomes, how can quantum information be transmitted from one particle to another without any physical travel, through a process known as quantum teleportation? How can information be transferred from one place to another without physically moving anything?
Not a particle, not a photon, not even a signal traveling through space. Just the state itself leaping from one location to another. At first glance, this sounds like pure sci-fi. Teleportation in real life? Moving the essence of a particle without moving the particle. But quantum mechanics doesn't care what sounds impossible. It allows something far stranger, the transfer of a quantum state from one particle to another across any distance using nothing but entanglement and a bit of classical communication. So the real question is, how can the universe allow information to move without matter tagging along? The tension ramps up when we hit the no cloning paradox, one of the strictest rules in quantum physics. It says you cannot copy an unknown quantum state. No duplicates, no backups, no photocopying quantum information. If you try to measure a quantum state too precisely to copy it, you destroy the very information you're trying to save. This creates an enormous problem. If you cannot copy a quantum state, how can you transmit it from one place to another? How can you move it without measuring it, without destroying it, and without violating the laws of physics? Teleportation sounds impossible because the very idea seems to require a perfect copy. But quantum mechanics, in its bizarre and elegant way, finds a loophole. Not by copying the state, but by transferring it wholesale. And that brings us to the reveal. Quantum teleportation is the transfer of a quantum state from one particle to another using entanglement. It works like this. You create two entangled particles, A and B. You keep B with you and send A far away. Then you take a third particle, C, the one whose state you want to teleport, and perform a special joint measurement involving C and A. This measurement destroys the original state of C, as required by the no cloning theorem, but it also instantly affects the entangled partner B. When you send the outcome of your measurement through normal communication, like a phone call or a radio message, the person holding particle B can then use that information to transform particle B into the exact quantum state that particle C originally had. The original state disappears from particle C and reappears in particle B. No matter traveled, no signal carried the state, only classical information moved, and the quantum state itself jumped from one location to another. The universe enforces the rules perfectly. No copy exists, the original is destroyed, and teleportation succeeds. This breakthrough is not theoretical. It has been demonstrated many times, even across kilometers using fiber optics and between ground stations and satellites. And the implications of teleportation ripple into one of the most transformative technologies of the 21st century, quantum cryptography. Because if states cannot be copied, and if measurements reveal themselves instantly, then quantum information can be used to create communication systems that are fundamentally unbreakable. Which sets up our next question. How does quantum physics make encryption keys that no eavesdropper can steal without being instantly detected? Why are quantum encryption keys considered unbreakable, so secure that even the supercomputer running for the entire lifetime of the universe couldn't crack them? Classical encryption relies on math problems that are hard, but not impossible. If someone had enough computing power or discovered a faster algorithm, even the toughest codes could eventually be cracked. But quantum cryptography flips the script entirely. It doesn't rely on mathematical hardness. It relies on the laws of physics themselves, laws that no computer, no machine, no trick can bypass. So the real mystery becomes, how can physics create a key that nobody can steal, copy, or read without instantly revealing themselves? The tension ramps up when you imagine an eavesdropper, someone trying to intercept the key while it's being shared. In classical communication, interception can be perfectly silent. Someone can tap a fiber optic cable, copy the signal, and leave without a trace. But in the quantum world, that's impossible. Remember the uncertainty principle and wave function collapse? If someone tries to measure a quantum state, they change it, they disturb it, they leave fingerprints all over it. That means that in a quantum communication channel, any attempt to intercept or copy the key inevitably alters the particles carrying it, and the sender and receiver immediately notice something's wrong. the very act of eavesdropping becomes detectable, guaranteed by the laws of quantum mechanics. There is no silent intercept, no perfect copy, no stealing the key without being caught. And that brings us to the reveal: quantum key distribution, the most famous form being BB84. Instead of sending numbers or classical bits, quantum distribution sends single photons prepared in different quantum states. These states encode bits, but they also carry uncertainty. If a photon is intercepted, its quantum state collapses. When the receiver measures the incoming photons, they compare a small portion of the results with the sender. If an eavesdropper has tampered with the photons, the error rate skyrockets. If the error rate is low, the key is safe. Because quantum states cannot be measured without disturbance and cannot be cloned, quantum key distribution ensures that any interference is caught instantly. Once both parties confirm that no eavesdropping occurred, they use the shared bits as an encryption key. And because the key was transmitted quantum securely, the encryption becomes unbreakable. This isn't theoretical. Banks, governments, and research labs already use QKD systems, and satellite-based quantum networks are emerging right now. And here's the exciting part. Quantum cryptography is only one piece of a rapidly growing ecosystem of quantum technology. Quantum computers, quantum networks, quantum clocks, quantum sensors. These aren't future dreams. They're real, being developed today, and they rely on the same strange quantum effects we've been exploring. Which leads us to our next question. How does quantum effects allow sensors to measure time, motion, and fields with mind-blowing levels of precision that classical tools could never reach?
How can quantum effects make measurements so precise that classical sensors don't even come close? Think about how we normally measure things: rulers, thermometers, cameras, GPS signals. They all rely on classical processes: light bouncing off an object, vibrations in a material, electronic signals in a circuit. But classical tools have limits. They get noisy, they drift, they wear down, and eventually they can't detect changes smaller than a certain threshold. Yet quantum sensors break straight through those limits. They can detect tiny shifts in time, gravity, magnetic fields, motion, and even fundamental constants with mind-boggling accuracy. So the question naturally becomes, how does quantum mechanics allow us to measure the universe in ways no classical device ever could? The tension grows when you look at what classical sensors can't do. Classical clocks drift over years because they rely on mechanical or electronic oscillators. Classical magnetometers can't detect the faintest magnetic fields produced by biological tissues or distant cosmic sources. Classical accelerometers can't sense movements small enough to detect underground structures or gravitational waves. And classical interferometers eventually hit noise floors, limits set by thermal motion, material imperfections, or environmental disturbances. Even the best classical instruments face fundamental barriers. But quantum systems, because they use the smallest building blocks of reality, don't suffer the same limitations. They don't rely on heavy machinery. They don't wobble with heat. They don't blur due to material defects. Instead, they use the pure, stable, predictable behavior of atoms and photons. The reveal is that quantum sensors exploit the most precise reference points in the universe, quantum states themselves. Atomic clocks measure time using the vibrations of atoms, usually cesium, rubidium, or ytterbium. These atoms absorb and emit light at incredibly precise frequencies. By locking a laser to that frequency, atomic clocks measure time so accurately they would drift by less than 1 second over the age of the universe. These clocks power GPS, define global time standards, and might soon allow navigation anywhere on Earth without satellites. Quantum magnetometers use spins of electrons or nuclei to detect unbelievably tiny magnetic fields. Some can measure fields 1 billion times weaker than a fridge magnet, small enough to map neural activity in the brain without touching the skull. Quantum interferometers use entangled photons or matter waves to detect tiny changes in distance and motion. With them, we can detect gravitational waves from black hole collisions billions of light years away. measure Earth's gravitational field with centimeter accuracy, or sense underground voids and ancient structures without digging. All of these devices take advantage of quantum superposition, entanglement, and coherence, phenomena that allow particles to oscillate in perfect synchrony, store information in stable states, or react to environmental changes with extreme sensitivity. Quantum sensors don't just improve measurement, they redefine what measurement even means. But here's the twist that sets the stage for something far bigger. The same quantum effects that let us build ultra-precise sensors today also shaped the entire early universe. Tiny quantum fluctuations, like the ones used in sensors, were stretched across cosmic scales during inflation, seeding the galaxies, stars, and structures that eventually formed everything we see today. Which leads us to the next massive question. What role did quantum physics play in the very beginning of the universe before matter and light even existed? What actually existed before cosmic inflation, before space expanded faster than the speed of light, before matter formed, before even the concept of before made sense? This question pushes us into the deepest mystery imaginable, the quantum origins of the universe. Classical cosmology can describe the universe after inflation beautifully, and it can trace cosmic expansion backward to incredibly early moments. But the instant we approach the starting point, those first unimaginable fractions of a second, classical physics collapses. Space, time, energy, and matter all reach extremes where Einstein's equations simply stop working. So the question becomes unavoidable. If classical cosmology can't explain the beginning, what was happening in those earliest moments? What filled the universe before it inflated into the cosmos we know today? The tension grows when you examine what happens when you push classical physics back toward the Big Bang. The density becomes infinite, temperatures become infinite, gravity becomes infinitely strong. Time itself approaches a singularity where earlier is meaningless. Classical cosmology predicts a point where space-time curves infinitely and laws break down. Yet the universe very clearly did emerge from something. These infinities strongly suggest that classical physics is the wrong tool for the job. The early universe was not classical, it was quantum. And because it was quantum, its earliest structure wasn't smooth or uniform. It was chaotic, jittery, filled with fluctuations born from uncertainty. Space was tiny, curved, unstable, and dominated by quantum mechanics. The classical picture of a neat, clean beginning dissolves under the reality that the universe emerged from quantum noise. And here comes the reveal that reshapes our understanding of everything. Quantum fluctuations seeded the structure of the entire universe. During the unimaginably rapid expansion known as inflation, tiny quantum jitters in energy, tiny wiggles that normally occur at subatomic scales, were stretched to cosmic sizes. Fluctuations that were once smaller than an atom became light years across. They froze in place as tiny variations in density, some regions slightly thicker with energy, others slightly thinner. Over billions of years, gravity amplified those tiny variations. The slightly denser regions became the seeds of galaxies, clusters, and large-scale cosmic webs. Every star, every planet, every galaxy, including the Milky Way, can trace its existence back to microscopic quantum wiggles in the early universe. The cosmos we see today, the massive structure spanning trillions of kilometers, originated from quantum randomness measured in billionths of a billionth of a billionth of a second. Quantum physics didn't just influence the beginning of the universe, it shaped it. The entire cosmic blueprint grew out of fluctuations driven by uncertainty. And here comes the pivot toward an even deeper idea. If the early universe was built on quantum fluctuations, and if those fluctuations follow probabilistic rules, not certainties, then the universe itself is fundamentally tied to probability, not deterministic outcomes. Reality at its deepest level is statistical, not absolute. Every event, every structure, every outcome emerges from quantum probabilities unfolding over time. That means to fully understand how the universe formed and how it behaves now, we need to understand the strange, rule-defying system that determines probability itself in the quantum realm. Which raises the next big question. Why do probabilities, not certainties, rule the quantum world? And how does the Born rule choose which outcomes become real? Why does the universe rely on probabilities instead of certainties at the most fundamental level? Why, when you measure a particle's position or momentum or spin, does the universe give you a chance of each possible outcome rather than a definite answer? In classical physics, the future is determined by the present. If you know all the forces and all the positions, you could predict exactly what will happen next. Planets orbit predictably. Pendulums swing predictably. Even chaotic systems, while complicated, are still governed by strict deterministic laws. But the quantum world rejects that idea completely. Instead of certainties, it gives us probability waves. Instead of fixed outcomes, it gives us likelihoods. So the question becomes, why does reality choose probabilities as its foundation? The tension deepens when you place classical determinism side by side with quantum randomness. Classical laws say, if you know enough, you can predict everything. Quantum laws say, even if you know literally everything about a system, its full wave function, you still cannot know what the next measurement will yield. You can only know the odds. It's as if nature itself is rolling dice each time a measurement is made. But these dice are not sloppy or chaotic. They follow exact mathematical rules. They're precise, predictable in their unpredictability. The wave function evolves deterministically according to Schrödinger's equation: smooth, continuous, perfect. But the moment you measure something, that smooth evolution breaks, and a single random outcome pops out. Classical physics has no equivalent. Nothing in classical science behaves both perfectly predictable and fundamentally random at the same time. This split between deterministic evolution and probabilistic measurement is one of the deepest tensions in physics. And here's the reveal that explains how quantum probabilities are actually determined: the Born rule. Proposed by Max Born in 1926, it states that the probability of getting a particular measurement outcome is equal to the square of the amplitude of the wave function at that point. In simple terms, if a particle's wave function says it has a large amplitude in one region and a small amplitude in another, you're more likely to find it where the amplitude is larger. This rule transforms the wave function from an abstract mathematical object into a direct predictor of reality. It tells us which outcomes are likely and which are rare. Without the Born rule, quantum mechanics would be a beautiful but meaningless mathematical structure. With it, the theory makes stunningly accurate predictions about everything from atomic spectra to chemical bonds to the behavior of superconductors. The Born rule is the bridge between quantum math and physical measurement. But the Born rule leaves us with an enormous question. Why does the universe square the wave function's amplitude to get probability? Why not some other rule? Why probabilities at all? Quantum mechanics gives us the formula, but not the reason. And this is where interpretations of quantum mechanics step in, each offering a different worldview. Some interpretations say the wave function collapses. Others say it never collapses. Some say hidden variables guide outcomes. Others say reality splits into multiple branches, which leads us straight to the next profound mystery. Do quantum events create new universes, or is the wave function's collapse an illusion explained by deeper interpretations? Does every quantum event create a new universe? It sounds like the setup for a sci-fi multiverse story, but it's one of the real questions physicists grapple with when they try to understand what the wave function and its probabilities actually mean.
If the wave function evolves smoothly and deterministically according to Schrödinger's equation, and if collapse only happens when we measure something, then what truly happens during a measurement? Does the universe split? Does the wave function suddenly jump? Does some hidden mechanism choose the outcome? Or are all outcomes real, just unfolding in different branches of existence? The quantum math works, but the interpretation of what that math says about reality is far from settled. The tension intensifies once you realize physicists don't all agree on what really happens. One group says the wave function collapses the moment we observe something. Poof, all other possibilities vanish. Another group says the wave function never collapses at all, and instead the universe continually branches into countless versions, so every possible outcome happens somewhere. Some argue that particles have definite positions and paths at all times, guided by hidden waves we can't directly observe. And some say the wave function is not even a physical thing, it's just a tool for predicting outcomes. These aren't fringe ideas. They're deeply serious attempts to explain why measurement yields one outcome and not another, why probabilities appear in a deterministic equation, and why observation seems to change the system. In quantum mechanics, the math is certain, but reality's interpretation is not. One of the major interpretations is the many worlds interpretation, which says that every quantum event splits reality into branches. If a particle could be here or there, the universe splits into two versions, one where it is here and one where it is there. Nothing collapses, all outcomes occur. Another is the Copenhagen interpretation, the one most textbooks teach. The wave function represents our knowledge, and when we measure something, the wave function collapses into a definite state. In this view, collapse is real but not fully understood. Then there's the pilot wave theory, or Bohmian mechanics, which says particles always have definite positions guided by a real wave that evolves according to quantum rules. No collapse, no branching, just hidden guidance that tells particles what to do. And there are others: cubism, relational interpretations, objective collapse theories, each painting a profoundly different picture of what's happening under the hood of reality. But here's where the story takes a crucial turn. Regardless of which interpretation you favor, there's a phenomenon that every interpretation must account for: quantum decoherence. This is the process by which quantum superpositions, the strange both-and states of particles, seem to disappear when systems interact with their environment. Decoherence doesn't rely on wave function collapse or branching universes. It's a physical process that happens whether or not someone is observing. And it's the key reason quantum weirdness fades as systems get larger and more entangled with the world around them. Which brings us to the next essential question: why does quantum strangeness vanish at human scales? And how does decoherence wipe out superpositions that should theoretically survive? Why does all the quantum weirdness, superposition, wave-like particles, entanglement, vanish the instant you move from the microscopic world to everyday objects? Why don't we see cars in two places at once? Why don't chairs exist as probability clouds? Why doesn't your coffee mug collapse into a wave of possible shapes when you're not looking? If quantum mechanics governs everything, not just tiny particles, then why does the world around us feel so undeniably classical? This is one of the biggest questions in physics because it forces us to confront why the universe looks classical even though it isn't. The tension grows when you consider how incredibly fragile quantum superpositions are. An electron can stay in a superposition of states for long periods, existing in multiple energy levels or multiple paths simultaneously because it is small, isolated, and easy to shield from disturbance. But the moment you scale up to something bigger, even something as small as a dust particle, the environment becomes impossible to ignore. Air molecules bump into it, photons scatter off it, thermal vibrations shake it. Every tiny interaction leaks information into the environment. And once that happens, the superposition collapses, not because of an observer's conscious mind, but because the system has become hopelessly entangled with everything around it. The environment measures the system billions of times per second, destroying quantum coherence long before a human ever gets involved. Larger objects interact so intensely with their surroundings that their fragile quantum states die almost instantly. Here's the reveal. Decoherence is the process that wipes out superpositions by entangling a quantum system with its environment. Instead of a particle being in two states at once, those states become linked to countless environmental states: photons, air molecules, vibrations, thermal noise. The system's wave function doesn't collapse in the strict mathematical sense. It becomes so entangled with the world that the distinct quantum states lose their ability to interfere. Without interference, superposition becomes meaningless. To us, it looks like the object chose one definite outcome, even though the underlying quantum description still contains all possibilities buried beneath layers of environmental noise. Decoherence explains why quantum computers must operate in ultra-cold, isolated environments. It explains why Schrödinger's cat can't remain alive and dead simultaneously. It explains why macroscopic objects behave classically, because their quantum states decohere almost instantly. And decoherence doesn't just make quantum weirdness disappear, it sets hard limits on what can be measured, how precisely we can measure it, and how classical descriptions begin to emerge from quantum rules. As systems interact with their environment, the very notions of time, distance, and measurement break down at scales where quantum effects dominate. Which leads to the next profound question. If decoherence erases quantum behavior as we scale up, what happens to our ability to measure time itself at the smallest possible scales? How does time behave when you zoom all the way down to the Planck scale, the unimaginably tiny realm where distances are so small and energies are so high that space and time may not even function the way we understand them? In our everyday world, time flows smoothly. Seconds tick by, clocks advance, events unfold in order. Even at the atomic level, time still seems continuous. But when you shrink reality down to the smallest slices the universe allows, something strange begins to happen. Time may not flow, it may not be smooth, it may not even exist in the sense we normally imagine. So the question becomes, what does time really look like at its smallest possible unit? The tension intensifies when you realize that our two best theories, quantum mechanics and general relativity, give completely contradictory pictures of time. General relativity treats time as a flexible dimension woven into space-time. It bends near massive objects, stretches, warps, and flows differently depending on where you are. It's smooth, continuous, and geometric. But quantum mechanics treats time very differently, as a parameter that ticks forward evenly, not something that bends or flexes. Quantum equations evolve in time, but do not explain time itself. And when you try to push these two frameworks together, when you try to describe time during the earliest moments of the universe or inside a black hole, everything falls apart. Relativity predicts smooth geometry, quantum mechanics predicts jittering, unpredictable fluctuations. At the Planck scale, about 10 to the minus 44th seconds, these descriptions violently clash. Neither theory can be trusted. Time as described by classical physics simply ceases to make sense. This leads to the reveal that some physicists believe time might be quantized, broken into tiny indivisible units, much like matter is made of atoms and energy comes in quanta. If time cannot be infinitely divided, then the smallest meaningful moment is the Planck time. Below that scale, the idea of one moment leading to the next loses meaning. The universe might tick like a cosmic clock, not flow like a river. Others propose that time isn't fundamental at all. It might be emergent, arising from deeper quantum processes, the way temperature emerges from the motion of molecules. In some quantum gravity models, time appears only when particles become entangled or when quantum systems decohere. In other models, time and space both dissolve into a network of discrete units where change happens in tiny jumps rather than smooth curves. These theories suggest that the flow of time is not an absolute feature of the universe, but a large-scale illusion that breaks down at extremely small scales. And here's where things become even more intriguing. If time becomes quantized or collapses entirely at the Planck scale, then the structure of space must also break down in a similar way. Time and space are woven together. You cannot fundamentally change one without affecting the other. If time comes in tiny, indivisible packets, then distance must too. And that leads to the next fundamental question: What happens when you shrink space to its smallest possible unit, the Planck length, and space-time itself begins to dissolve into something new?
What happens when you shrink space down smaller than 1.6 times 10 to the negative 35 meters, the Planck length, the smallest distance that has any meaning in physics? Below that scale, our normal understanding of space simply falls apart. You can't picture it, you can't imagine it, you can't even measure it because measurement itself stops making sense. If you try to probe distances smaller than the Planck length, the energy you'd need becomes so immense that you'd create a tiny black hole right where you're trying to take the measurement. So the question becomes, what lies beneath that scale? Is there a below at all, or does space-time simply stop existing in the way we think? The tension rises sharply once you remember that space-time in general relativity is a smooth geometric fabric. But in quantum mechanics, nothing can remain perfectly smooth. Everything fluctuates, everything jitters, everything has uncertainty. At the Planck length, these two pictures crash into each other. Quantum mechanics demands that space-time fluctuate violently at tiny scales, while relativity demands smoothness. The result is catastrophic. Space-time becomes so distorted, so chaotic, so violently curved that it may not even behave like space anymore. Distances lose meaning, directions blur, geometry tears, reconnects, and foams. The universe becomes a storm of quantum gravitational fluctuations, tiny distortions popping in and out of existence faster than light can travel a single Planck length. This is where the idea of space as a continuous fabric fully collapses. And that leads to the reveal. The Planck length marks the boundary where known physics breaks down and quantum gravity takes over. It isn't just a small distance, it is the lowest rung of the universe's ladder of meaning. Below it, concepts like left, right, near, far, before, and after lose coherence. The Planck length is not a smallest piece of space, it's the scale where space itself ceases to be well-defined. This is where theories like loop quantum gravity describe spacetime as a discrete network of finite loops, and where string theory imagines vibrating strings whose smallest excitations define the structure of everything. No experiment can currently probe this regime, but the math tells us something unmistakable. The Planck length is the frontier of physics. It's where quantum fluctuations of spacetime rival gravitational curvature. It's the scale at which gravity itself must become quantum, whether through gravitons, strings, or some deeper unknown description. And here's where things get truly wild. At the Planck scale, even black holes behave differently. If you compress enough energy into a region smaller than the Planck length, you could create a quantum black hole, a tiny, short-lived object that flickers out through Hawking radiation almost instantly. These micro-black holes may have existed in the early universe, and they may hold the key to uniting quantum mechanics and gravity. Which brings us directly to the next question. How do black holes behave when they shrink down to subatomic sizes, smaller than atoms, smaller than protons, shrinking all the way toward the very limits of spacetime? We're used to thinking of black holes as giant cosmic monsters in space, swallowing stars and bending galaxies. But what happens if you compress enough energy into a region so tiny that gravity and quantum mechanics collide head-on? At that point, a black hole is no longer a giant cosmic beast. It becomes a quantum black hole, a microscopic object where the rules of the quantum realm take over completely. And this leads to some of the most baffling questions in all of physics. Can a black hole this small hold information? Does it evaporate in a flash? Can it even exist stably for more than the tiniest sliver of a second? The tension explodes when we confront the paradoxes that appear at this scale. Classical black holes trap everything, even light, inside their event horizons. But Stephen Hawking's work showed that black holes actually emit radiation. If a microscopic black hole radiates energy, it should shrink and evaporate. But if it disappears completely, what happens to the information about everything that fell in? Quantum mechanics says information can't be destroyed. Relativity seems to allow it. This creates the information loss paradox, a conflict so severe it suggests that our understanding of space, time, and physics itself is incomplete. Add to that the fact that at extremely tiny scales, space-time becomes foamy and discontinuous. The event horizon of a quantum black hole isn't a smooth surface, it's jagged, shifting, fluctuating with quantum noise. Does the interior of such a black hole even exist in any classical sense? Or is it replaced by something entirely different, like a fuzzball or a quantum remnant? Every attempt to merge quantum mechanics with general relativity
inside these tiny objects leads to contradictions that shake the foundations of physics. Then comes the reveal. Quantum black holes are hypothetical but deeply important because they bring together all the forces and rules of nature at once. If enough energy is squeezed into a region at or near the Planck length, a micro-black hole might form. Unlike their massive cousins, these tiny black holes would evaporate almost instantly through Hawking radiation, emitting a burst of particles as their mass converts back into energy. They may have existed naturally in the earliest moments of the universe when energies were incredibly high, or they could appear in extreme particle collisions far beyond what our technology currently achieves. In some theories, micro-black holes don't completely vanish. They may leave behind stable Planck-scale remnants that store information. In others, the event horizon dissolves into quantum fuzz, eliminating the paradox altogether. These tiny black holes are not just curiosities, they are windows into the deepest workings of reality, where quantum laws and gravity intertwine so tightly that neither can be understood separately. And this brings us right to the doorstep of the final question in our journey. After tunneling, fluctuations, quantum fields, entanglement, superposition, collapse, decoherence, Planck-scale chaos, and microscopic black holes, what is the quantum realm telling us? What does all this strangeness reveal about the true nature of reality? Is the universe fundamentally solid or probabilistic? Is reality built from objects or from information? That leads us into the final segment, what the quantum realm ultimately says about the nature of reality itself. Is reality at its core certain, solid, and deterministic, or is it fundamentally probabilistic, fluid, and shaped by information rather than substance? After traveling through wave-particle duality, superposition, entanglement, quantum fields, vacuum energy, tunneling, decoherence, Planck-scale foams, and quantum black holes, this question hits harder than ever. Everything we've explored points to a universe that behaves nothing like the world our senses show us. So what is reality actually made of? Is it matter? Is it energy? Or is it something deeper, something built on mathematical rules, probabilities, and the invisible structure of fields? The tension rises as we look back at the contradictions and mysteries we uncovered. Particles that act like waves, waves that behave like particles, objects that exist in multiple states at once until we measure them, forces carried by virtual particles that pop in and out of existence, gravity, the most familiar force of all, refusing to follow quantum rules, time that may be discrete, space that may not be continuous, vacuums that aren't empty, fields that extend everywhere, entanglement connecting distant particles instantly, the universe seeding galaxies through quantum fluctuations, and the collapse or branching of wave functions deciding which version of reality we get. These aren't small details or mathematical curiosities. They're foundational. They show us that the classical world we experience is just one layer, an emergent illusion built on top of something far stranger. The reveal after everything we've seen is this. The quantum realm tells us that the universe is not built from solid matter, but from probabilities, fields, and information. Particles are just ripples in fields. Forces are exchanges of virtual messengers. The vacuum is an ocean of activity. Reality doesn't choose outcomes until interactions force it to. Space-time itself may be emergent from deeper quantum structures. What we consider objects are stable patterns of information held together by quantum rules. The solidity of matter is a consequence of exclusion principles and field interactions, not little marbles locked together. The classical world is a special case of a much more flexible, probabilistic universe. Behind every stable object, every measurement, every event, lies a storm of quantum possibilities collapsing into outcomes we can finally observe. And here's the final hook, the thing to leave lingering in your mind. If reality at its core is built from probability waves, quantum fields, and information, then what does it truly mean for something to exist? Are we seeing the universe as it is, or just a version decoherence allows us to perceive? What other layers of reality might be hiding behind quantum rules we barely understand? And if the quantum realm is the foundation of everything, what discoveries still wait for us when we push deeper? Because this quantum journey doesn't end here. It's just a beginning. In future videos, we'll explore what consciousness might have to do with quantum mechanics, whether time itself is an illusion, how quantum computing may reshape technology, and what the frontier of quantum gravity could reveal about the universe's ultimate structure. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.